Computer-aided education of structural mechanics, and finite element method, using VisualFEA. A presentation produced by Ji-Young Lee.
VisualFEA is a finite element analysis program with a special feature of computer-aided education. This presentation introduces a new paradigm of teaching and learning structural mechanics and finite element method using VisualFEA. This introduction exemplifies only one topic from each of the two subjects, although the program covers a number of educational topics. Most textbooks of structural mechanics are full of equations, formulas, diagrams and example problems. There are a number of important concepts and procedures that should be mastered from these textbook materials. Instructors deliver their knowledge and ideas to students through oral explanation, drawings on blackboard, and example problems. Accordingly, students study the subject by grasping lectures, reviewing textbooks, and solving example problems. This conventional pattern of teaching and learning may not be appropriate for the goal of mastering the concepts and procedures of the subject. The computer-aided instruction takes the advantage of fast computing capability, graphical visualization and user-friendly interface of modern computer technology. Instructors may make use of the facilities in presenting their lectures with instant problem-solving, data visualization and realistic simulation of structural behavior. Students also can easily access the facilities and manipulate interactive simulations, observe the visualized response, and inspect the computational procedures. Various experiences obtained using computer facilities may help students to gain better understanding and interest in the subject. Therefore, the computer-aided education is an effective approach for enhancing the degree of understanding about the concepts and procedures in structural mechanics. VisualFEA is a finite element analysis software with a special feature for computer-aided education. The software is a monolithic program integrated with all the ingredients of finite element analysis for structural, geotechnical, heat transfer and seepage problems. The current version covers the education of two subjects, structural mechanics and finite element method. Its implementation is based on the intrinsic components of finite element analysis, namely, element modeling, equation assembling and solving, pre- and post-processing, and other user interfaces. The components are reorganized into educational features such as visual representation of concepts, indication of mathematical relationship, interactive operation of computing process, experiment with data manipulation, and simulation of model behavior. The educational functions available in the current version are classified as topics in two subjects: structural mechanics and finite element method. The topics related to structural mechanics include the following items: mathematical relationships in structural members, relationship between internal forces and stresses in structural members, force application and resulting structural behavior, Moore's circle, yield surface, influence line, moving load, and buckling modes of structural members. The topics related to finite element method include the following items: element equations and stiffness matrix, assembly and solution of global stiffness equations, shape functions and interpolation, stress recovery and smoothing, eigenvalues and eigenvectors of stiffness matrix, dynamic modes and vibration analysis, adaptive analysis procedure. More topics and subjects will be added in the future versions of VisualFEA. However, this presentation introduces briefly only two of them, distinguished by black letters. One topic from structural mechanics, and the other from finite element method. The usages of the functions listed here are fully explained in screen demos, prepared for each of them. The first topic is the mathematical relationships in structural members. There exist mathematical relationships between external force, shear force, bending moment and displacement. The relationships are graphically manifested, and can be examined through interactive operation of the diagrams. Let's take an example of a continuous beam with 3 spans. The image shows the first screen that appears at the start of a 2-dimensional frame analysis. A 3-span beam can be modeled simply by clicking grid points. Then, material properties and member sections are assigned to the model. The nodal boundary constraints are defined as a roller or hinge. Lastly, the external forces are applied to the beam members. Now, the results of the beam analysis can be represented by diagrams, using the diagram menu items: shear force diagram, bending moment diagram, and deflection diagram. Multiple diagrams can be displayed simultaneously by overlaying them. Each of the diagrams can be dragged independently and separated from the overlaid image. Now, we will observe the relationship between diagrams. If you place the screen cursor at a point on the shear force diagram, a yellow tick box shows the information about the shear force at the position. If you click the point, there appears a green line, connecting the applied force diagram and shear force diagram. It is indicated in the 2 diagrams that the shear force at the point is equivalent to the summation of the forces left side of the green line. At the same time, the line tangent to the bending moment diagram is drawn, and it shows that the slope of the tangent line is equivalent to the shear force. If you drag the green line, the value of the shear force changes, and the indication of the relationship is updated instantly following the green line. The slope of the bending moment diagram is also updated. If you click another point on the shear force diagram, there appears a new green line. Now, there are 2 green lines. It is indicated the difference of the shear force between the 2 green lines is equivalent to the summation of the forces between the 2 green lines. This represents the mathematical relationship between the external forces and shear forces. As you move any one of the 2 green lines, then the representation of the relationship is also updated instantly, following the movement of the green line. It is also indicated that the difference between the slopes of bending moment diagrams at the 2 points is equivalent to difference of the shear force. This implies the mathematical relationship between the shear force and bending moment. If you place the screen cursor at a point of the bending moment diagram, a yellow tick box shows the information about the bending moment at that point. If you click the point, there appears a green line, connecting the shear force diagram and bending moment diagram. It is indicated in the 2 diagrams that the bending moment at the point is equivalent to the highlighted area of the shear force on left side of the green line. At the same time, the line tangent to the deflection diagram is drawn. The slope of the tangent line is determined by the area of bending moment diagram. If you drag the green line, the value of the bending moment changes, and the indication of the relationship is updated instantly, following the green line. If you click another point on the bending moment diagram, there appears a new green line. It is indicated in the diagrams that the difference of the bending moment between the 2 green lines is equivalent to the highlighted area of the shear force diagram. This implicates the mathematical relationship between the shear force and the bending moment. As you move any one of the 2 green lines, the representation of the relationship is also updated instantly, following the movement of the green line. The display shows the angle between the tangent lines of the deflection diagram at the 2 points. The mathematical relationship between bending moment and deflection can also be observed using deflection diagram. If you place the screen cursor at a point of the deflection diagram, a yellow tick box shows the information about the deflection at that point. If you click the point, there appears a green line, connecting the bending moment diagram and deflection diagram. The area of the bending moment diagram on the left part of the green line is highlighted in blue color. The slope angle of the deflection curve is proportional to the highlighted area of the bending moment diagram. The angle is represented in radian. If you drag the green line, the slope angle of the deflection curve changes, and the highlighted area is updated instantly, following the green line. You may select a portion of the beam by clicking 2 points on the deflection diagram. The boundary of the selected portion is represented by 2 green lines. The area of the bending moment diagram in the selected part is highlighted in blue color. As you move any one of the 2 green lines, the representation of the relationship is also updated instantly, following the movement of the green line. The difference between the slope angles at the boundary is determined by the highlighted area of the bending moment diagram. The mathematical relationship between the bending moment and deflection can be observed using this function. The bending moment reaches local maximum, or minimum value, at the points of zero shear force. In order to observe this relationship, select the shear force diagram and bending moment diagram at the same time by rubber band selection. Then, there appear green lines connecting the 2 diagrams. The green lines connect the 0 crossing points in the shear force diagram, and the corresponding points in the bending moment diagram. These are the points where the first derivative of bending moment as well as the shear force falls to 0, and accordingly the bending moment reaches the local maximum, or minimum. If you move the applied point force, all the diagrams are changed simultaneously, and the green lines are moved in accordance. However, the green lines always pass through points of 0 shear force and points of minimum maximum bending moment. The next observation is the relationship between the 0 bending moment and the deflection curve. In order to observe this relationship, select the bending moment diagram and deflection diagram at the same time by rubber band selection. Then, there appear green lines connecting the 2 diagrams. The green lines connect the points of 0 bending moment in the shear force diagram, and the inflection points of the deflection curve. Again, while moving the applied point force, the diagrams and the positions of the green lines are updated instantly. The green lines always pass through points of 0 bending moment and inflection points of the deflection curve. These are the points where the second derivative of deflection falls to 0. The internal stresses in structural members are evaluated from the internal forces such as axial force, shear force and bending moment. The bending stress can be computed only in the case the geometry of cross-section is specified. This is an image of bending stress overlaid with the bending moment diagram for the 3-span beam. The bending stress is computed from the bending moment using the formula, applying the cross-sectional geometry of the beam. The stress image can be rendered in 3-dimensional view. The geometry of the assumed cross-section is applied in this 3-dimensional rendering. If you click a point on the stress image, a new window opens, with the image of the cross-sectional stresses at the point. Dragging the cursor along the beam spans refreshes the image of bending stress for the updated cross-section at the cursor point. If you place the cursor over the cross-section image, a yellow tick box shows the value of the bending stress and y distance from the neutral axis. As an educational exercise, the displayed numerical values can be confirmed, using the formula to compute the bending stress from bending moment. This was a brief introduction about the educational function related to mathematical relationships in structural members. More detailed explanation can be obtained from the screen demo about this function. The next topic of the educational function is concerned with finite element method. The function is intended to examine and simulate the overall procedures of computing element stiffness equations, assembling them, and solving the system equation. If you select an element from the finite element mesh, by a mouse click, there appears a list box window with information about the element stiffness matrix. The window contains the computational details of the matrix, arranged in hierarchical tree. The contents can be expanded or collapsed by clicking the small triangular buttons. The first item shows the geometry of the element, with the nodal coordinates. The second item is the properties assigned to the element, and the resulting constitutive matrix. Each of the data item can be switched between numerical and symbolic expressions by clicking the item. The contents of the matrix can also be displayed symbolically using mathematical expressions. The next item shows the numerical integration scheme, including the integration weight, natural coordinates, and Cartesian coordinates of each integration point. The shape functions and their derivatives can also be expanded with the Jacobian matrix and its inverse. This example shows switching the Jacobian matrix into symbolic expression. You may expand the strain nodal displacement relationships and numerical integration of the stiffness matrix for each integration point. The last item is the element stiffness matrix, obtained by summing the values of all integration points. The element stiffness matrix is assembled into the global stiffness matrix, entries of which are represented by small squares. The red squares in the global stiffness matrix represent the entries, with assemblage of the element stiffness matrix. The nodal degrees of freedom associated with the assemblage can be identified in both element and global stiffness matrix. If the manual assembly button is pressed, the process of stiffness matrix assembly can be simulated manually by drag and drop operations. Click an element from the mesh, drag the element, and drop it in the global stiffness matrix. Then, the element image turns into squares representing matrix entries. The entries are spread and assembled into the matrix. If the numeric mode button is pressed, each entry is represented by its numerical value instead of a square. The hidden part of the matrix can be accessed using the horizontal or vertical scroll bar. The assembly of system equations can be simulated in 3 different schemes, namely, square matrix, skyline and frontal schemes. The original square matrix is represented by its upper triangle for comparison with other schemes. Each of the assembly schemes can be examined through simulation in manual or automatic assembly mode. Here, only the frontal scheme will be illustrated in more detail. The data storage for this scheme is divided into 2 parts, that is, the main memory and auxiliary memory. The assembled stiffness matrix and force vector are stored in the main memory, and the Gauss eliminated equations are stored in the auxiliary memory. The assembly process can be simulated, either automatically or manually. The manual simulation is useful in observing the characteristics of maximum frontal length, which is the factor determining the memory requirement, and computing time. Select an element and assemble the element matrix into the global stiffness matrix in the main memory by drag and drop operation. As more elements are assembled, the frontal length changes. Once there appear degrees of freedom with complete assemblage, the corresponding rows and columns of the matrix go through Gauss elimination. The data for eliminated entries are moved to the auxiliary memory, and the space of the eliminated entries is vacated for next assemblage. The assembled degrees of freedom are increased by a new assembly, or reduced by Gauss elimination. Thus, the frontal length fluctuates while the assembly is going on. The element for assembly can be selected in arbitrary order. Through a few trials with different order of assembly, we can easily notice that the maximum frontal length depends on the order of element assembly. Similar experiments can be made also for the cases of square matrix and skyline assembly. In these cases, the memory requirement is determined by the half bandwidth, which varies depending on the node numbering. Thus, this educational function is useful in understanding how the half bandwidth is affected by the node numbering. and how the maximum frontal length is determined by the element numbering. This was a brief introduction about the educational function related to computing and solving finite element equations. More detailed explanation can be obtained from the screen demo about this function, with examples of frame analysis and plane stress analysis. The free version of VisualFEA can be downloaded from www.visualfea.com. The screen demo files can also be downloaded from our FTP site ftp://visualfea.chonbuk.ac.kr. This is the end of the presentation.